Good afternoon, everyone. Or is afternoon? Yeah, it's noon. It's afternoon. It's 1 minute after noon. Let's see who's in the chat. We're going to click the button right here. Whoa, it's just made a live stream. Jesse, good to see you here. Chapter 14, based on meteorological data. Let's go take a look at that. Let me get MuBot started up. Here we go. And start that right there. Going to live chat, pop out. Okay. There's that. We're good to go. My hair's all floopy today. I don't know what's up with it. It's the front is a little bit longer, so it's like it's all crazy. Okay. MuBot's awake. Throw out some MuBot points. There's a chatbot update, but I am not updating MuBot till after the semester ends. MuBot will not be updated. We saw we had some OBS problems yesterday. I went to do my in the first class. If you watched the first class, I did a presentation. I usually do a like court trial where MuBot tries to bring me to trial and say that I'm guilty of giving out too many points, but then it wouldn't do the freeze on MuBot because I updated OBS. And I was like, well, I didn't do that for the second class. We did a little bit different, but I was hoping to do my usual like MuBot brings me to court and I freeze and like wait, MuBot didn't give out the points. There we go. Now MuBot's giving out the points. Never update your software, your hardware during the semester, because then all of a sudden you run into problems. Chapter 14, is that homework or quiz, Jesse, did you say? Chapter 14 quiz, right there. Jesse leading the way on points. We're gonna need some new point levels. Been going a little crazy on the points lately. I really want to reinforce to people like hashtag show up to class because it's super duper important. It's super duper important. Show up to class. That's how to get the work done. You don't show up to class. Good to know, yeah. And let me get we're going to be right here in just 1 second. There we go. Getting booted up. Okay. You said it is Stat 201, Chapter 14, quiz, and this is meteorological data. Based on meteorological data. Okay, let's go take a look at this. Full screen this. Here we go. Let's go find it. Okay, look at how many questions there are. Woo! When's this one due? I need to look and see when it's due. It's a good question. This one is due on... Why doesn't it show me the date over there? Because I want to talk about the T next time in class. It's due on the 18th, a week from today. So that's a good bit of time away. That's good right there. We've got a lot of time. Next Tuesday, I think, right? It's got a lot of time. This is, I think I just closed it. Oh, because I went out of it. Darn it. So this is gonna, have you learned about the T yet? Because I've keep mentioning it in class. I'm keeping like, well, we'll talk about this. It's not a big concept. T's are basically like Z-scores. This is just kind of an introduction before we get to the homework. I got the homework done yesterday. Nice. Homework done today. What's interesting about T-scores is they're basically like Z-scores. So since I know the Z-scores for a 99% comp score is 2.5758, oh, nice job right there, Jesse. Great job. Yeah, we go over it in, the past videos and stuff, and that's always a good way. And then I want people to show up to class, and then we give the theory in class, and we go in detail. So Z-scores are always the same. T-scores are based on degrees of freedom, which you probably saw the T-distribution gets smashed down. It has larger tails. There's questions that even mention that. I'm just going to mention this briefly, then we'll do the meteorological. But the great thing about knowing Z-scores are basically T-scores and T-scores are basically Z-scores is that I can kind of take guesses at these. Now, this is the hardest one to guess. It says 2 decimals. That's a harder one. Higher degrees of freedom makes it more like the Z. So 98 is 2.3263. So this is going to be 2.3, and we'll go 6 right there. And we might have got both, or nope, we just got 1. So this is the one that's really hard to guess, probably. Yeah, that's the one I'm not going to get by guessing. But, yeah, what is this? Going to be even higher? Yeah, that's the one I can't really guess because it's, so many. It's hard to get that second decimal. Well, yeah, I could go look it up, but T's are basically like Z's, and I can get it right. This one right here, I got right because I know the Z-score. I know the Z-score of that one. It's hard to guess. We can talk about that problem another time, but let's go find the meteorological one. And I keep eating this flaxseed granola. It's very good, but flaxseeds making me cough. Okay, based on meteorological data. Does this one use jump right here? Oh, 2.90? Jesse on fire. I was so close. Oh my gosh. Look at that. If I had just gone up one more, I think it would have given it to me. Oh, look at how close I was. I was like, it's got to be up there. Does it want to the exact decimal? Here, let's find out real quick, Jesse. We should be close at 99% confidence with 12 degrees of freedom. And then here, I'll re-timestamp this in a moment because we've kind of gone on a short tangent on this. Okay. Student T, and then you enter in 12 degrees of freedom, 99% confident between 3.05. There it is right there. And so that's how you do it. So it was even higher up. But yeah, yeah, great job, Jesse. Yep. And so the thing is if you have enough degrees of freedom, and this is what I was kind of mentioning, I know the z-score is 2.5758. So as degrees of freedom get higher, the curve goes towards the 2.5758. So it never technically reaches it. You'd have to get infinite degrees of freedom. But as you go towards more and more degrees of freedom, it goes towards 2.5758. Ooh, I need to show. Oh, whoa. It shouldn't have done. I don't know what's going on there. That is not correct. So I'll have to watch out when I'm showing this in class I'll need to tell Adam this. I'll send him this video to say, as it approaches infinite degrees of freedom, it should go to 2.5758. There must be some sort of overflow or something happening with the app right here. No one usually enters in this many degrees of freedom, but that is not theoretically correct. It'll go towards 2.5758. And then we can see the extra decimals right there. Ooh, 2.5758. Oh, so something weird is happening. There's the 2.5758. And the reason I know this, last thing on this, and we'll re-timestamp here, is that is the z-score for a 99% confidence interval. So the t-score approaches the z-score 2.5758. So that's how I knew that number is I'm like, well, the z-score for a 99% confidence interval is 2.5758. As degrees of freedom increase, the t-score approaches the z. After about 100 degrees of freedom, they're close to identical, and most people just use the z-score instead of a t-score. But software will use the t-score for you, so you don't have to worry about doing the calculations. So it's kind of a moot point because the t-score will be calculated for you, and it'll use the t-curve, but they're basically z-scores, like basically. We'll talk about William Gossett and the t-curve and Mr. T. So yeah, that's really, maybe let me timestamp this like t-scores, learning about t-scores. Let me retake your question. Then we're going to do your question right here. Thank you, Jesse, for being here. Learning about t-scores. Okay. So now we're at the 9:43 mark. Statue 1, chapter 14 quails, based on meteorology. Sure. More t-scores. I have fun doing those. Then what about the t-distribution? Meteorological. Is it a jump question? Is it like, let's see here. I think this one's a jump one where you have to use jump. Meteorological. It's an interpretation question. Cool. Okay. So this looks to be confidence interval interpretation with exact wording. Now, what we need to do whenever we get a confidence interval here is we need to think about what are the parts of the confidence interval. So we have here, they are saying, based on meteorological data for the past century, a local TV weather forecaster estimates that the region's average snowfall, winter snowfall, is 17 inches. Good to see you here, Isaac. So that is going to be their estimate. Now, what we want to do is we want to take this information and make it relative to the mathematics we are doing. So the mathematics we are doing is going to be, in this chapter, with confidence intervals, we are doing y bar plus or minus t with n minus 1 degrees of freedom. That's a subscript right there, s over square root of n. So with this, what are we looking at right here? The estimate is 17 inches. That's what they're estimating the average snowfall will be. See, it says average right there, y bar is average. So the average snowfall is 17 inches. Now the margin of error is everything over here after the plus or minus. It's all put together into one calculation right there for them. The 95% confidence is relative to the t. That's why we usually put a star on the t, saying what percent confidence relative to. They don't really give you much more information about this other than we're creating a 95% confidence interval to estimate the average snowfall. And then we would say it's somewhere between 14 to 17 because the interval is 17 plus or minus 3. And so this is the lower, and this is the upper of the interval. And what we want to do now, and this is what I beg everyone to do, is to write your own interpretation. So the reason we're doing this right here is because the reason we're doing Pearson is to learn how to do the test and know how to do this in practice if we have to do it in a class or for disciplines. Confidence intervals are very common. We were just looking at research this weekend on cheese and yogurt and health benefits of them, and they had confidence intervals. So I was like, oh, look at those confidence intervals right there. And my wife was like, wait, they're confidence intervals? Like, yeah, they give you the estimate right there, and there's confidence intervals. Look at all that stuff right there. So they are used throughout a lot of science. And she was like, oh, yeah, I see it now. So with this right here, I am blank % confident that the true blank is contained in the interval blank to blank. So once again, I hope you're watching, I think if you're here right now, I think you're watching the video. But if you're in the future, once again, we're about to solve the problem right here and figure out the answers. But it's not about just solving this problem. It's about knowing what this interval means. We have right there the estimate, which is the weather person is estimating 17 inches. They have a uncertainty boundary of plus or minus 3, which is known as a margin of error. And so we would say I am 95% confident that the true average snowfall this region will get is contained in the interval 14. Oh, someone should catch my errors. Jesse saw it in that moment. Right as I was saying it, Jesse, 500 points for catching errors. Right as I was saying it, I was like, something's wrong about that. Because the 17 plus or minus 3, it's easy to make errors like that. But when you start looking at it and reading it, you're like, wait a minute, 17 plus or minus 3 is 14 to 20. So just check your work. We often make mistakes. This is where people make mistakes on their interpretation for the second part, is they say true proportion. We're saying true average snowfall or true mean snowfall. And it makes it clear up here because it's talking about average, and that's going to be testing. Yeah, exactly. And so you're like, wait a minute, I didn't go to the upper. This is not proportions because it's quantitative, which is something we should note, like how much snowfall on the ground is quantitative versus like did snow fall today is the proportion of days it snows in a year. So we could say the true proportion of days it'll snow in Knoxville. That would be categorical, like did it snow today? Or we could say the true average snowfall in Knoxville in a given year. That would be a quantitative question. So now when we look at this right here, they're going to give some interesting interpretations. During 95 of the past 100 winters, the region got between 14 to 20 inches of snow. No, this is not about 95% confident doesn't mean 95% of the winters it got. No. This is about the true average snowfall during a season. So this statement is incorrect. The interval, here we go. This one basically says it. The interval is for the population mean of snowfall, like the true average snowfall, not the snowfall for individual winters. So it's not about one season, it's about on average. I think so. The interval means this. No, we're not doing a forecast. Yeah, so that's not about individual winters right there. It's on average, because this would just be one observation. There's a 95% chance that the region will get between 14 to 20 inches of snow this winter. Same sort of problem right here. It's talking about one winter again. It's on average, so it's not about one winter's snowfall. It's on average we get this. So there we go. This statement is incorrect. The interval is for the population mean snowfall, not for predicting the snowfall for individual winters. That sounds accurate to me. Yeah, it doesn't estimate just for the years in the sample. There will be between 14 to 20 inches of snowfall on the ground for 95% of the winter days. So it's not about individual winter days. It's on average for a season. This statement is incorrect. The interval is predicting the average. No, not for next. The accomplishment only estimates what happens in the year. No. And I hear. This statement is incorrect. The accomplishment was based on a sample of snowfalls amounts for several years, not the amounts of snow on the ground for sample days. Yeah, great job, Jesse. Automatically doing it. Residents can be 95% sure that the area's average snowfall is between... This one sounds a little better. I am 95% confident. This might be accurate. What's wrong with this one? Yeah, is it? Let me look at the next one because the next one would have to be wrong then. Residents can be 95% confident that the average snowfall during the past century. No, we know what the average snowfall. This is the sample. So we are not we know what the sample is. So that's probably going to say right here. This is incorrect. It is given that the original is given. Yeah, well, oh yeah, it's given. That's what we know. That is the sample estimate right here. Wow, Jesse, yeah, that's right. So this was what we learned from the past century. So we know the answer to that. We know the answer for the sample data. This one right here, residents, I am 95% confident that the average snowfall is contained in the interval 14 to 20 inches. So yeah, it looks correct. I think we got everything right. There we go. Jesse, I thought you were helping me double check my answers right there. Great job, Jesse. So the last one, a lot of people wonder why the last one is wrong. Once again, we know what the average snowfall was for the last century. We don't have to estimate what the average snowfall is. Like if I go out and talk to 100 people, I don't have to estimate what the sample's average is. That is Y bar. So mathematically speaking, Y bar right there is from the past century. So we know what the snowfall was for the last century. So we're not trying to make a comp snow for the last century. Yeah, well, you were guessing correctly. And then knowing why it is, like why why some answers are wrong is very important. Because you might say, well, why wouldn't that last one be correct? It's because the interval is not made to estimate for the sample data, which they reiterate a lot throughout that. The interval is made to estimate the population, like for all winter seasons, kind of outside the sample data. And then assuming the sample data is representative, which the problem with this is it's a time series question because things can change, like, global warming, things like that can definitely change the snowfall in a region. So, yeah, so that it's a really good question, good on interpretations. And that's where you want to think like, why is this question wrong? What are we creating? And then you want to write your thing down here, like I am 95% confidence the true average snowfall in the region is contained between the interval, blah, 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 blah. And then you can see right here, the residents, like I am 95% sure, I like to say confidence, that the average snowfall is between blank to blank. I was like, yep, that sounds like what we got right there. And then this one just really throws you for a loop when it says the average snowfall during the past century. That's not the population of what we're trying to understand. We're not trying to understand the sample data. And that's where the problem is with this one. So you have to be very careful, very exact with your wording. And yeah, great job. Which other one should we do, Jesse? These are really great questions. That's why, I try to do a little more in depth than just like, here, let's show the answers. It's like, okay, what does this mean and why? I like it. Oh, is this oh yeah, which is the true about the family T? Let's talk about the T distribution. I think I saw that, right? I think it's question 3. Cool, this gives us a little bit of time to talk about the T right here. And which of the following are true about the T? Let me mark this. This is a really good one. It'll be really quick, but wait. Stat 201, chapter 14, quiz. Which are true about the T? Okay. Unimel and symmetric, has degrees of freedom, thicker tails. Boom. Okay, let's talk about that. You ready? Let's talk about this and understand this. Now that we know the answers, let's think about it. The T is basically the Z. But we got this guy, William Gossett, who worked at Guinness Beer. So let me bring up Gossett and Guinness Beer. Gossett and Guinness Beer. So this guy right here, William Gossett, worked at Guinness Beer. And he's even got a plaque right there, chemist, statistician, chief brewer. And everyone loves talking about Gossett and the T distribution. And Jesse, what is this curve? It's saying the T right there, but that T curve, that's actually 2 curves if you can't tell. The T curve looks a lot like the what right there. What is that T? This is the T curve right here. It looks a lot like the what, wouldn't you say? I mean, we've learned another curve. Looks a lot like the normal. So here's what Gossett noticed, is when Gossett took small samples, his intervals were off. And that's when and this is the theory behind it so you can understand, when you take a small sample, you might not get what? Think extreme values that are unlikely or rare. If you take small samples, you might not get what's in your data. If you take small samples, you might not get what. So if we have some data over here, and we take like 5 observations, you might not get what? What might you not get? We'll maybe bring this one in a little bit more. If you take small samples, you're probably unlikely to get many what's in your data. Things far away from the rest of the data. I'll say it right here. Outliers. So if you don't get outliers, you might be underestimating the standard deviation. Does that make logical sense? Like, if something was an outlier here, it would greatly increase the standard deviation. But if you don't get the outliers, because smaller samples are less likely to get extreme things that are unlikely, then you're going to underestimate the standard deviation. And since you're underestimating the standard deviation is part of the confidence interval formula. And by having a smaller standard deviation, there it is right here, the what will be smaller. If the standard deviation is smaller, what will also be smaller? And I circled what will also be smaller. If the standard deviation is smaller, what will also be smaller? So I've circled what will also be smaller. The margin of error. So that means you're underestimating the variation, or like the like uncertainty in your interval, right? So what William Gossett did is he created something called the T distribution, which has in it degrees of freedom. Now, the degrees of freedom basically tell you which T you are using. And that's a huge note to take, is that the degrees of freedom, the formula here for this one is n minus 1. So that's n minus 1 is equal to the degrees of freedom, tell you which T you are using. Making it a family of distribution, that was the first thing we learned right there. So you notice right here, if we go over to the T, it's going to first ask us how many degrees of freedom are there. So we might say, oh, there's 20 degrees of freedom. And notice the curve changes. Exactly, Jesse. The degrees of freedom tell you which T you're using. And basically, this makes it a family of distributions where there's just a ton of T curves. There's all different T curves with different degrees of freedom. There's basically infinite T curves. You can even put in decimal degrees of freedom. It'll only matter really down here. So you notice now it's actually changing, because after you get to a high enough amount of degrees of freedom, the T curve looks basically like the what? With a high enough amount of degrees of freedom, the T curve basically looks like the what? Watch as degrees of freedom go up again, the T curve starts to basically look like the what? Like now, for all intents and purposes, just the normal curve. So it really matters. And think with the formula n minus 1. So like if we had a sample size of 10, what would be the degrees of freedom now? With a sample size of 10, what are the degrees of freedom? 9, exactly. So the T curve is going to have the most dramatic differences when the sample size is much wider. The T curve is going to have the most dramatic differences from the normal when the sample size is much wider. Smaller, exactly. And that's what Gossett was counterbalancing here. When you have these small samples and you might not truly understand the variation in your data, he created this distribution, which is like a correction to the normal curve. So the T curve is basically a more exact normal curve that gives us more precise intervals, because Gossett noticed that his 95% confidence intervals were not containing the truth 95% of the time. He looked over the long run. He's like, my intervals don't contain the truth 95% of the time. And I'm saying I'm 95% confident that in the long run, these intervals contain the truth, but they don't. So he corrected it. So once again, the T curve is basically the normal curve. It's a family of curves that all have their own degrees of freedom. It's called the student T distribution because he published it under a pseudonym. I've heard many different stories how like people weren't accepting his work, but he called it the student T distribution. Student was just a fake name he used. So students T is what it's called, but William Gossett is the guy who created it, worked for Guinness Beer, and it's got thicker tails with lower degrees of freedom. The tails have more area in it. It's more narrow around the center and has thicker tails, and then it starts to approach the normal curve as it gets more degrees of freedom. I think that covers all the concepts we saw on the screen right here. As the degrees of freedom increase, T approaches normal. Very important right there. T has fatter tails and more narrow in the center, and it's unimodal symmetric. Basically, the normal approaches the normal, and larger differences with lower degrees of freedom where it's more narrow and thicker tails. Yeah, and I really like that right here. You can literally see it. If you put your degrees of freedom to 1, you can then increase this right here, and you can see it approach the normal. Does that make more sense, Jesse, right there? And this is what we'll use for a T interval. And there's the T interval right there, and we'll also use it for a T test. Yep. So that's William Gossett, who invented the T distribution. And so just knowing that right there, so for all intents and purposes, it's basically the Z. basically. And what's really great, chapter 14, yeah, let's do one next. So when I do work like this, all I have to do right here is t.test on the data, and there's my t interval. So you see it literally calculates, that's the t for the test, that's not the t for the t interval. It literally gives me the t interval right here, and I could say I'm 95% confident whatever I'm estimating the true mean for it is contained in the interval blank to blank. All I had to do was t.test. And then I can say like, testing the value of 0, we would fail to reject with a p-value of 0.07. I do not reject whatever we're testing the true mean is equal to 0. I can do mu right here, right? I could hypothesize that the true mean is 10. There we go. So I would not reject 10. There we go. Oh, and because 10's in the interval too. So I would not reject 12. Because 12's in the interval. So I wouldn't reject 12. Let's do in 1998. 1998, a year that I remember well, but probably people in class weren't even born. Oh no. Oh, Jesse, that's where I start. I used to be like, haha, you were born in the 90s. Not like haha, but like, oh wow, you're born in the 90s. And now I'm like, you weren't even alive in the 90s. It's man, I was in college when 9/11 happened. So like now people are like, yeah, that's what I thought. Don't worry, it's like it's when you start to feel old. That's like when you're like, oh man. Start talking about like I don't remember the 80s really well. Like the 80s are like I don't remember the 80s. I remember the 90s quite well. But 2000s, I remember everything in the 2000s. That was was it 1882? But like my nephew who's like 7, he was born in like 2015 or so, or 20, he might be turning 8 this year. I mean, he is. So yeah, he's born in 2015 then. In 1998, we got some data right here. Yeah, so I mean, he's he'll be like 9/11. That's way before. That's old, Uncle Brian. Oh, yep, I'm older than you. Okay, this one right here. Let me mark the time again. This one is best done with jump. So I highly suggest having jump open and ready to solve this question. So we'll talk about how this would look on a test, but we wouldn't generally give you data like this because what are we going to need to solve to make a t interval for this? Because this is where we're going with this, is we're going to make a t interval. There's the t interval down here. What are we going to need? Like what components do we need? Here we'll grab the question. And we're not, once again, going to really worry about what it says yet. We're just going to talk about how to make a t interval and what we need to make a t interval. And then we're going to go ahead and find that. So what do we need? Oh, great. Jesse, yeah, you're on fire right there. And it says we opened up, what is this? A sample of 1, 2, 3, 4, 5, 6, 7, 14 bags, right? Is that 14 bags? Looks like 14 bags to me. And so the equation is y bar plus or minus t star n minus 1 degrees of freedom. Check out the t thing we just talked about. S over square root of n. And the n minus 1 is the degrees of freedom since it's n or 14 minus 1. Then degrees of freedom equals 13 because that's the degrees of freedom right there. So the issue with this question is, at least the way it's worded, it wouldn't really make, great job, Jesse, 100 points right there. It wouldn't really make for an amazing test question right now, but I could turn it into a test question pretty easily if I go over here and I just copy your data. Give me a second right here. I'm going to go over to jump and we're going to solve some answers right here. But we're going to think about how it would look as a test question also. So here we go. We got our jump license accepted. Now, when you're in jump, you always want to go to File, New, Data Table. Now, people love to click inside of there. Don't click inside of there. So hopefully don't click inside of there yet. We're going to have to go over to the question and click the drop-down menu under the Data tab. And with the drop-down menu, we're going to click it, copy to clipboard. And then once you copy to clipboard, hit Control-C or Command-C on a Mac. Now, I want you to notice something. There is no column name at the top of this. Sometimes there is. Take note if there is a column name or not a column name, because that's going to be very important when you go back to your spreadsheet and you go Edit. You see how to paste with column name. There was not a column name at the top, so we don't want to do that or it'll look wrong. So don't do that for this one. You have to remember, was there a column name? Did it say something at the top? Because this one did not. We're just going to paste. So every time you paste, make sure it looks correctly. It didn't put like the first number at the top. You will get the problem wrong if you put the first number in the name of the column. The first row of data should be the first observation of the data. So make sure it looks correctly. This one is just a regular paste, which can be Control Command V. Don't paste with column name. You can add a column name if you want, not required, and call it something like chips right there by double clicking and calling it chips. Not required, just names the variable. So now we're going to use the correct variable right here, and we have the data. You can also type it in if you want to, but that can lead to errors. You should have 14 rows of observations. Now, to turn this into what a test question would generally look like, we'd have to go here to Analyze, Distribution. Make sure it's blue for chips over there on the far side. It means quantitative. So you see it's blue right there. Double-click chips, and then click OK. Now, I'm going to go here to Stack to make it look all nice and pretty right here. There we go. The red arrows have your options, and we have all the information. We might even have the 95% confidence interval. But let's take note of what all this information means. So this is a lot of data right here. I know, right, Jesse? That basically solves most of the question. So most of the question is solved just by doing that. And if you need, let me just mention this right here. If you need something other than 95% confidence, go to the red arrow and then go to confidence, not that one. Where's confidence interval? Confidence interval. We don't want to fit a distribution on it. You can go to other or use 99, 95, 90. Other allows you to put in what you want. Don't use known sigma or one-sided intervals. We're doing the two, like a normal between interval. These are other concepts right here. That's a Z interval, and those are one-sided intervals. We don't talk about those here. So you could put something like 99% confidence, and it'll give you the 99% confidence interval. So that's the lower and the upper. Yeah, it's just like, just calculates them like that. Just instantaneous calculations of the intervals for you. So that is how you can get something outside of the 95% confidence interval for the mean. This is a 99% confidence interval for the mean right there. We'll just remove this for the time being. But let's talk tiny bit about what you have here in this output. Knowing your notation is super important. Right here, you have Y bar, because remember, these are all summary statistics, which means they all came from your sample, which makes this your sample size. This is your upper for the interval. This is your lower. This is your standard error of the mean, which is actually S over square root of N. And this is the standard deviation right here, which is just S. So know your notation, and this is 5-number summaries over here. This is all the 5-number summary right here, and then there's other percentiles in the data, but that's the 5-number summary, 5-num sum. Good to know that. The min, the max, the Q1, the Q3, the median, all that good stuff. We won't be using that, but here's all the data we need to know and know the notation for it, because the standard error is actually really good right here. Yeah, it does all. Yeah, it's nice when it does all the math for you. And watch this, Jesse. I can estimate the margin of error of this interval by taking this value right here and rounding it down to 26 and timesing it by 2, and the margin of error is a little advanced right here, is about this. The margin of error is kind of close to this of the interval. Now, if you remember how to do the margin of error is always what? The length of the interval. So if we have right here the lower, and we have the upper, and we have the center of the interval. The center of the interval is Y bar. So 1, 2, 3, 7, I'm just rounding. And then the upper is 1, 2, 9, 4. And then the lower is my estimate off? Oh, because the T. Oh, that was not a great estimate. I should have put we'll put it down here. We'll say, darn T interval. Darn T. Should have rounded up a little bit more because it's the T. We'll round up to about, well, we'll do 52. It's the T interval, so we need to use the T statistic. But the margin of error exactly is half the length of the interval. So this is a margin of error. This is a margin of error. We're just kind of showing some concepts here to make sure we understand what we're looking at. Like, we are marking all the data with the numbers we see on the screen, showing our interval, and then we can actually calculate the exact margin of error with some decimal rounding. So, haha, exact. And we can subtract the upper from the center. And there's the margin of error. It's 57. Not quite 52, but decent-ish. So now it comes down to, well, what would a test question look like? Well, we do give output on the test like this. So that's why I'm talking about this right here, knowing what you're seeing on the screen. So don't calculate it using my 2 trick because that's for z-scores. That's when you have a z-score. The t interval right here. And Jesse, why was our t so different from the z? Because the what is what? Why is our t so different from the z? And then let's solve for the interval here, and then we'll finish off the problem. Why is our t so different from our z here? The sample size is small. Exactly. So smaller sample size means there's going to be t and the z differences. So we have to go over here, put in the degrees of freedom 13, and the t is 1 point. That's not right. Between. There we go. Mirror confidence intervals are between 2.16 right there. Great job, Jesse. And we do, yep, Savannah, we can do that one. And so 2.16 it was, right? 2.16. So that's the t, which is relative to the percent confidence. That's what the star means. And you know what, Jesse? Do we really have to solve s over square root of n? That's the standard error, right? Like s over square root of n is the standard error. So we can just plug in the standard error. So we could just put that value right there if we want to do that. Yeah, it's given. That is the standard error. You can double check it if you want. You can go square root of 14. So we can go square root 14 and take standard deviation of 9.47, divide by it, and there's the standard error. So we can just plug it in. Oh, Jesse, good question. We'll do that one here after. We'll do Jesse's question, then we'll hop to Savannah's because we're in chapter 14 at the current moment. And then we can take right here. So if you do solve out all this, you will get those answers. So you can take this, solve by 2.16. There's the margin of error we calculated more exactly. You can add that to 1236.8571 and get the upper of the interval. And there it is right there. Basically the same. They might have carried extra decimals. We didn't, but 1,294.94. You can subtract the margin of error. That wasn't the margin of error. But make sure to solve this interval and practice doing this, and you will get these numbers right here. So that is how to do it by hand, but Jump did the work for us. So don't think of Jump just doing the work for you. That is how test questions could look, where we give you the data and we want you to solve it. Okay, so let's take a look at what it asks first here. Now we're going to solve the question. Independence condition, I basically wrap into the what. I always wrap the independence into the what condition, first condition. I always wrap my independence, because if it's independent, it would need to be this. I always wrap independence into what condition. I've mentioned it, I think, a few times in class. Like sometimes I'll say, well, sometimes I kind of allude to an independence condition, but I just throw that into the what-ish condition. I do like the way they phrase this here. And the answer is basically right here in these answers. I always wrap my independence condition into what? What do I basically... Does independence deal with the 10% or the random? Independence, if it's random, it's independent. So the data from a random sample, someone can assume independence, which you're fine to do. Now it wants us to construct a histogram. You can actually, can you deduce the answer? Great job, Jesse, right there. 100 points in the chat. Me about loving some randomness. You probably need to do Jump for this, but you can look at the data. Well, it goes up to 14. I think it's got that one. It's probably this one. It looks to have data centralized around here, but you're really best to do it in Jump. And, you know, it doesn't look perfect like this. What you need to do is these bin widths are 100. So you need to double click this. Hopefully you made your data in Jump. Change it from 900 to 1600 units of 1,000. And then go down to here. And it looks best. Ooh, we're between like 2 now. Should look. Oh, that's not. That should go to. Oh, it's got the double tick mark. Minor ticks 0. Is that gonna... I always dislike the way Jump... There we go. Okay, good. And I'm pretty... Oh, wait. Ooh. It's this one, isn't it? Wow. That's mean. That's mean. That's such a minor difference. That is not fair. This one has just a little bit of more data over here. So I guess you could actually look, if you really wanted to check, there are 1, 2, 3, 4 observations between 11 to 1200. So 1, 2, 3, 4. There's the 4 observations. where this one shows more observations over here. This one shows 1, 2, 3, 4, 5. Oh, but that's, yeah, 11 to 1200. Yeah, so that's tough right there. That's small difference where, yeah, and then you could check the observations. So you could do it by hand by looking at how many observations are in a bin and looking over here and then counting the observations. So you don't technically need jump, but if you correct your number line like I did, there's the settings I did, 900 to 1600, remove the minor tick, and then it will show you the shape, and then just be very careful because there are two similar ones. And you could double check like I did. Okay, evaluate the histogram. So this is actually, and this one I do get wrong sometimes because we are going to use the T. So that's where I've made small mistakes on this one, the evil questions. I just don't like the way they phrase it. So be careful. Don't click the answer I'm about to click here. I'm like double guessing myself on this one because any question I know I've gotten wrong in the past, then I'm like, oh, so I should do this because I've gotten it wrong. But then I reverse my answer. The point of this question is we're checking the what condition right here. The point of this question is we're checking the what condition. So Jesse, what are the 3 conditions to make a T distribution? We haven't gone over them so much in depth, but it's quantitative data. So what are the 3 conditions? What are the 3 conditions for the T distribution? We'll have a slightly different name for it, but you kind of know it by something else right now. So condition 1 is always random. Condition 2 is 10%, which they didn't really check, but they alluded to right there, the 10% condition. So you have random, 10%, then you pause, and it's quantitative. Good. Savannah, yep, random. And then this time it's technically known as, that is correct right there, large enough N, but that's part of what we call the nearly normal condition. We pause before saying the next one. And since this is how many chips are in the cookies, then we're going to do nearly normal, which includes large enough N. I'll be going more over it next time. Great job, Jesse, right there, the nearly normal condition. So that's what they're saying right here. Since it's basically unimodal and symmetric, one can assume, it should mention that, it probably... so the data we use, the T distribution is used for calculations. The population would follow the normal. I'm like double, triple thinking myself. It's not bimodal and symmetric. The only plausible answers are this and this right here. And that is the nearly normal condition. Don't click that answer. Wait till we get finished with this question. Don't click that answer in. 95% confidence interval. Once again, this is the easy part because we did it ourselves, but also we have jump here to check our work. 1 decimal. If you get a decimal place wrong, just let me know. That's the lower, that's the upper. 11794. Pretty sure I got that one right. I'm going to think it over if I got it wrong. 1294.3. Okay. What if mine looks bimodal? But does it? It shouldn't. Did you change the bins on the bottom? Because the bin widths can drastically change the way it looks. Like the bin widths right there are going to make it look a little bimodal, but this is still a centralized area around here, but the bin widths can drastically change how it looks. So you could be like, oh, that's trimodal, but it's just the bin width's probably deceiving you. And what we usually like to do is do a normal quantile plot. You see how that follows the red line. So that's a really good question there, Jesse. In truth, what we would probably want to do, and we'll mention this when we talk about the nearly normal condition, is do something like a normal quantile plot. It follows the red line, so it's pretty normal. Or you could always do a goodness of fit test to check to see if it's normal. And the goodness of fit test comes back with a high p-value for both of them. How do you do bin width again? You can change bin width right here by double-clicking the number line. We're going to go back to the pointer, and we're going to double-click the number line. And then we're going to go to min 900, max 1600, increment 100, minor tick 0, and save it. So just double click that right there, and you can adjust your histogram to be a certain bin width and look a certain way. And that's a big reason why we use the normal quantile plot, because the normal quantile plot does not have bin widths. It shows us the red line of what the normal should be. And then if our points follow it, and a little kind of give to say like, well, it's within kind of the expected range of what the normal would be from our observed to what we would expect on the normal quantiles, like the percentiles on the normal going up here on z-scores. Yeah, the minor tick. Yeah, that's what I didn't do first either. I always forget where that's at. I had this right here, and that created a little bit of a bimodal shape. And then I did that kind of quickly right there. I was like, okay, good. Yep. I wish it just said like, I mean, we said we want to go from those in, there's the minor tick. You can probably add a whole bunch of these in. Look pretty interesting. Now there's 3 minor ticks. Yeah, don't do that. Okay, so I think we got both numbers correctly. What does the confidence interval say about Nabisco's claim? Now, does this mean one bag will have 1,000 chips? Like if someone said, my bag of cookies doesn't have 1,000 chips. Well, yeah, one bag might not have 1,000 chips, but on average, we would expect the bags to have 1,000 chips because I am 95% confident the true mean amount of chips found in a Nabisco bag of chips, Nabisco cookies bag, is contained in the interval 1,179.4 to 1,294.3. I am 95% confident the true mean amount of chips found in Nabisco cookies. It's not about one bag. It's about on average for Nabisco bags. That's a big thing, and they really illustrate that down here. Because the confidence interval is entirely above 1,000, the mean number of chips per bag is likely more than 1,000. However, the normal model predicts that a small number of individual bags will have fewer than this. No, will not mean every bag. Not every bag. Here we go. This one right here. Because the interval includes, it doesn't include. Did we get? We did! Whoa, I've gotten this one correct. Yay! I learned how to do that question. We did it. I was double guessing myself because I was like, I literally double guessed myself and just thought through the theory of it. And I was like, okay, the population would follow the normal. The population doesn't follow a T. The student T is used to model and create intervals. We're saying it's nearly normal, which is the condition. So I literally was just like repeating the theory to myself as I was answering that question. I was like, okay, so theoretically, we're saying it's nearly normal, that it should follow the normal curve because of the unimodal symmetric shape of the data. And we will use the student T interval when creating the estimates. It's not, the population doesn't follow a student T. Student T's are based on sample sizes and degrees of freedom, so they don't really deal with population. They're used to create intervals to estimate the truth for a population. So they deal more with the sample, which is why degrees of freedom are from a sample. Woo! Really good question right there, Jesse. Here, we'll do your next one right here. The speed of light one. I think this is a pretty crazy one. And then we'll do Savannah's question. So this is the 1882, right? Oh my gosh. That was a really great question, Jesse. Like, if you follow through that question, you basically if you can do that question, you basically understand the full chapter. That is like with what we did right there, that is a full understanding. Is that Michelson? What is his name? Michelson. Okay, let's check out that speed of light question. I think it was way back here. That's not sampling distribution, is it? Better not be. What did I just see? I don't even know where it went. Is that sampling distribution? Yep, we'll be going over the T way more next class. A lot more on the T. It's basically the Z. That question's really good. It's really quick, too. Okay. Oh, this one has like a trick to it, if I'm trying to remember right, Jesse. Okay, let me timestamp this, and then Savannah will do your question next. Thank you so much, Savannah, for being here. Savannah, 100 points. Great work. Okay, make sure we got the right timestamp. Okay. 5033. Let's do this. Okay. So with this question right here, when you think about the speed of light is quantitative. So that means we're doing the T interval. Well, let's say things like Mr. T is mean. I'm sure he's a super nice guy. But we say Mr. T is mean because T intervals are for the mean. He's mean if you're doing drugs. Don't do drugs. Watch that PSA from Mr. T. It's an awesome 80s PSA. And Mr. T is awesome. And so we go right here and we take the data and we notice this is a 98% confidence interval. So basically, this is practice on making a 98% T interval, and we need to know what we're doing. So we've got the equation right there. We'll rewrite it here in a second. Once again, you are given the equations on the test. But Savannah and Jesse, what is going to be the hardest part for a lot of people if they get an equation like this? They need to know their what. You need to know your what anytime you're doing an equation like this right here. What's up, Sloan? Gig 'em, Sloan, right there. You need to know that notation.
Notation, brother.
Another 100 points for everyone in the chat right there. You need to know your notation. You got to know what Y bar is. Y bar is the sample mean. T star, great job, Savannah, right there. All these points. T star means the T statistic relative to a certain percent confidence with n minus 1 degrees of freedom. That is a calculation right there telling you which T from the family of T's it comes from. S being the sample standard deviation and N being the sample size right there. So we know everything in this equation. Very important because we're going to have to find it here in this problem to solve it. Now, they do a little bit of weirdness on this, and we're going to double check our answers right here in a moment. We see 98% confidence. So let's go for the easiest thing to solve that is usually tougher for people. 98% confidence means that's the confidence of the T. Now, we also need to know what the T, the degrees of freedom. So the degrees of freedom are from 23 trials. So what are the degrees of freedom? What are the degrees of freedom? So we're just looking for this T, which is relative to 98% confidence, and it has 23 sample size it came from. What are the degrees of freedom? So DF, degrees of freedom. What are the degrees of freedom? What are the degrees of freedom? Yeah. Yeah, we did it last week. We could do that. I think it's due next week, right? Yeah. Thank you, Terry, right there. He did upload those. Terry rocks. I moved back the date a little bit. What are the degrees of freedom? It's n minus 1, n is 23. What are the degrees of freedom? What are the degrees of freedom here? Mubot's already helping us out with the apps, where we'll go next. The degrees of freedom are 22. Yep. So take a moment right here, and I want you to tell me the T statistic. So this is practice that you know how to solve these problems. What is the T statistic? I can guess for you. My guess of the T is 2.42. That's my guess. How close did I get? I guess 2.42. I'll show how to find the answer in a second. See if you can go to the apps page and find the T statistic. That's just a guess over there. I have a guesstimate of what it should be always. The reason, if you're wondering why you're looking this up, how I was able to guesstimate that, I know the z-score is 2.3263. Well, that's the z-score. Good job, Sloan, right there. That is the z-score. And Jesse has the t-score, which is always a little bit further out than the z. And it approaches the z as degrees of freedom increase. So check this out, Sloan. Are you ready? When we do the t, it's basically like the z. So you have to go over here, and you have to say, I want to use the t-curve. So you go to the t-curve, you put in your degrees of freedom, which your degrees of freedom here are 22. Then you put in your percent confidence, and there's the t-score right there. So it's close-ish. But the t-curve is a more exact calculation based on the degrees of freedom, which are usually calculated with sample size in some way. Yep. So this is the t-curve right here, and this is, so Jesse gave us 2.508. So that was close-ish, but more exactly. And great job, Sloan, right there. That's how I was able to, yeah, the app is really cool. Thank you, Adam Spanbauer, right there. That's, I was able to guesstimate it from the Z curve, the Z you mentioned, because I know the T is always wider. Jesse, are you kind of seeing how I'm able to guess these? Sometimes I'm like, okay, degrees of freedom are kind of low, so maybe I should add a little more extra. If it had been like 100 degrees of freedom, I would have been like 2.36. Watch this. 100 degrees of freedom, 2.36. Because it's basically 2.3263 at that point. So that's how I'm able to guess those a lot of times and be like, oh, it's about this. 1,000 degrees of freedom, 2.33. Because it's going to be super close to it. 1,000 degrees of freedom. There you go. It just approaches 2.3263. And so with this right here, yeah, Jesse, awesome. We'll do waist sizes a little bit, and we'll do Savannah's question first here. Thank you, Jesse. Excellent work. And so check this out later. We have the standard deviation of 107.116 square root of 23. We're just plugging in the numbers up above, plus or minus 756,216. So excellent work right here. And the more you understand these problems, the more it doesn't seem like magic. You're like, oh, well, just take the numbers, it says, and abide by that. There's that. So now we're finding the margin of error right here. Margin of error is 56.016. And 756.216. Now we're just going to add and subtract that. And there it is. How many decimals does it want? I think it's doing it. It also moves this 233. We'll hope that that's enough decimals. We'll hope. Minus 700. There's the lower, there's the upper for the interval right there. Okay, so the thing is, and I got to remember how it wants us to input this data. We found the answers, but there's a little bit of a trick. Okay. They have subtracted this from the numbers. So when we do the true mean speed of light, we need to add back on that numbers if I'm correct right here. This is where we need to take the interval we have and add back on 299,000. Sigh. Okay. Yeah, so they're basically subtracting off all those extra digits. So all we have to do is put 299 before all this. So because they've subtracted that off. So that's one number there, and that's the other number. Once again, make it a contiguous number. There's the number right there, and that's a decimal point, not another comma, because they've subtracted that off from them. That's a decimal. Okay, so I'm going to put this over here to the other side of the screen so I can see it while I write these down, make sure not make some errors on them. But they subtracted the 299 off of it, which won't change the standard deviation. It would just change the mean. So we're just readjusting. We're recentering the data around the original mean. Preferably, you wouldn't do this. I think they're just making it easier on calculations, but you could have just had that on. Like if you went back here, if you had the 299 back on, it would just be right there. And you could do that when doing the calculation. And then if you notice, it's not going to change the margin of error. It would just change the center of the interval. The center of the interval now being right here, plus or minus this amount. So you could just do it that way and make sure to add and subtract. I think we've done all the work correctly. It looks accurate to the data. There we go. And it wants to 2 decimal places. This is where we always make mistakes. Don't worry, I make them 2 right here. Double check 2 decimal places. It will get angry if you enter in a 3rd decimal. In other words, what does 98% confidence means? This means when we do repeated trials of 98% confidence intervals, we will see in the long run, 98% of 98% confidence intervals contain the true mean. Dr. Enes has such an amazing app right here that he sent out to us. Really cool to watch this in work right here. So thank you to Dr. Enes Ozil, who sent this out. And it really shows what it means to be 95% confidence or 90% confident. We can go right here. We could put this up to 98% confident. Oh, I wish they just let you type in the number because that's such a small. There we go. And then here we'll increase the sample size a little bit right here. We'll go to 10 sample size. And then we'll start making intervals. So it's sampling 10 observations, and we're making 98% confidence intervals. The true mean is right here. And what we will see in the long run, I let this simulation run a long time in class, is that 98% of these intervals created from samples of the population are going to contain the truth. Funny enough, right now, none of them have not contained the truth. Every time it makes one, there's 2% probability in the long run that the interval, well, oh, there's our first one. And you see right here, wow, we're exactly at 98% of the intervals. It did it like perfectly on cue. But you will see if you were to do something like, let's change it down here. It should reset it to, there we go. If we go to 95% confident, we could hit something like an interval not containing the truth at the start. Oh, whoa, I called it. But notice the probability is actually approaching 95%, and this is actually the law of large numbers. So it's not about one interval containing the truth, because the interval will contain the truth or not contain the truth. Darn it, that one does contain the truth, just barely. Really? That looks like it doesn't contain the truth. Oh, there's one that doesn't contain the truth. Also, I wanted you to see here that the variation in the sample, like that one had more variation, creates a larger width to the interval, and that's the standard deviation. So if we get a sample, that one had big variation. If we get a sample with very little standard deviation, you'll see a smaller margin of error, like that one right there was a good example. So it has a smaller margin of error due to a smaller standard deviation, the value of S. So you're actually seeing the values being computed for you right there. Well, it's figuring them in the background. N was always 10. S is going to be bigger or smaller based on how wide the data is, because that's what the standard deviation is, the spread of the data. And then the mean is actually the center dot right there. So the Y bar is actually that dot right there. There's Y bar from each of the samples. So it really shows you what's going on right here and how 95% confidence means in the long run. Okay, so which one of these kind of goes with that? With 98% confidence based on the data speed of light, no. For all samples, 98% of them will have a mean speed of light that falls within the confidence interval. The confidence interval contains the true speed of light 98% of the time. Well, the confidence interval either contains it or doesn't. So any measurement of speed of light will fall. No, we're not talking about the measurements. With 98% confidence based on these data, the speed of light is between that's about the best right there. B does sound good. I don't love their interpretations right there. I would say I am 98% confident the true mean speed of light is contained in the interval blank to blank. So that's about as good as we get. I am 98% confident the true mean speed of light is contained in the interval blank to blank. What assumptions must you make in order for this to work? Let's see here. Independent, I wrap into the random a lot of times, so we need that. Random sample right here. Uniform. Do we ever talk about data being uniform? Do we ever talk about the data being uniform? We don't. We talk about the data being unimodal and symmetric. Nope. We don't want uniform data. And then the samples drawn from a large population. We don't care about really the population size. I'm iffy on that one. Are they gonna? Nope. Because the only thing here, and this is where they could try to, I don't love that this one exists, is because you could have a problem with the 10% condition. If you draw from a very small population, then you could. So that one, I was a little like, I don't usually assume that, but that's where like it's like, well, is that really wrong? What would it give us if we had clicked that? Someone can be like, Brian got wrong. 70, it gives you the full thing wrong? That's mean. Because what are our three conditions right here, Sloan? If you remember the three conditions, you can basically get all these correct. Three conditions are random, 10%, so it doesn't even mention 10% right there. So random and independent. Independent needs to be met if it's random, like it is met if it's random. If independent, it's pretty random. Hey, what's up, Phil? Good to see you here. And then we have here that the data follow the unimodal and symmetric distribution, which is the nearly normal condition. So really good stuff right there. We have Savannah's question next, and then Jesse's question. Savannah asked, where'd Savannah's question go? Shoot, Savannah, which question did you have? There's been so much talk that I can't scroll up enough. Jesse had one more. Jesse was wondering about the. I think I might be able to find the one, Savannah. I should have marked it. Actually, do that. Oh wait, here it is. Environmental agency. Environmental agency, and then let me mark Jesse's other question. An environmental agency. There we go. And then Jesse's other question was. California researchers measured waste sizes. That one shouldn't exist because that one's a sampling distribution question. But this one isn't success failure though. Why is this one? So really quick on here. Yeah, thank you, Sloan, right there. Why is this one not success failure? Why is this one not success failure? Because we're measuring the speed of light, and the speed of light is what? So this won't be success failure. Really good thing to notice on this question. This one's not success failure because we're measuring speed of light, and speed of light is what? Great job, Sloan. Good. And that just, this is the practice right here. So when you get to the test, you're like, oh, speed of light is quantitative. So it's going to be, and it's kind of large enough n, we'll call it nearly normal. So exactly. And Savannah, great work right there. Also quantitative. Let's go do Savannah's question right here. Okay. So we got Savannah's question right here. Thank you, Savannah, so much. And excellent work. Really good practice. It really comes down to repetition with these chapters. These chapters are not chapters you learn overnight. They're not chapters where you're like, the test is tomorrow, I'm going to do it. You'll be like, what in the world am I learning? These are ones that after practice, you're like, yeah, it makes sense. I know how to do this. It's like playing a song on piano. If you try to learn a song on piano the night before, you might get it down, you might do decently, but really it comes down to practice makes better, and you will understand how to do these more when you create a routine for them. If you notice, we usually don't look at what the question says. We focus on how to solve the question first. So we're like, okay, well, what is this question actually? Skip the on that question. An environmental agency. Okay. Let's do it. Okay. Savannah, what do you think is going to be the key to solving this problem? And Savannah, great work. 100 points. Thank you for all your help and work. What do you think is going to be the key to solving this question? Boom. Savannah knows for another 100 points. It's going to be that notation.
Notation, brother.
Okay, so we got that notation, brother, in the chat. Let's go right here and figure it out. Any notation on the screen, Savannah? Give me one bit of notation. I'm gonna start writing some stuff for you to help you out, and give any notation. Oh, we're doing interval. Great job. Wait. Is P hat 2% though? Good work, Savannah. Is P hat 2%? So it says N is 400. I mean 40. Yep, it's margin of error. And you know what? This is the margin of error. That is the margin of error because it's everything after the plus or minus. So we don't have to worry about the start of the interval. We'll just solve this right here because we're just solving for n. Great job, Sloan, right there. And let's show how Sloan solved that right there. We'll go to the apps. So this is how Sloan got the z-score right there, which is, I'm going to do 1.645. I'm going to do an extra decimal. There we go. I usually carry them to 3 decimals. You can carry to 4. 2 is decent, like 2. So Sloan, another 100 points. 2 is pretty good. Oh, it already has it on the screen. Oh, because we're doing, yeah, we need to go to between and go to that. And we're doing the const interval, which is the between values. We put in 90%. I like to carry to 3 decimals usually. You could do 4, 1.645. And this is how Sloan found the value, is go to between, put your confidence, make sure it's z-scores, make sure you're doing the normal curve right here, and you will get the z-score of 1.645 right there. So there's the z-score, so we know what the z is. And we're still missing a value or 2. I'll solve them here in a moment, but we're still missing a value or 2. So we know all these values right here. What are we missing? We're still missing a value or 2. This question is best handled as a notation question. So they pick 40 cars and find that 4 have, we're missing, well, Q hat technically, and we're missing P hat right now. We're missing, well, we can get Q hat and P hat, but how would we get Q hat and P hat? And what are these things? What do these things mean? Well, but these are, we don't know P, we definitely don't know the truth. That's what we're trying to estimate with this interval, right? Trying to estimate the true amount of cars with faulty engines, the true proportion, excuse me. But P hat is the sample proportion and Q hat is the sample proportion. Yeah, Savannah, we're throwing you 500 points. So what is P hat? That's exactly where you want to get, Savannah. That's worth 500 points. And you say, oh, you see what we have, right? Because we have 4 out of the 40 cars had a problem. So what is P hat? I think you see it now. You've stated it in the chat. I'll start writing it because you've said it. So P hat is this. What is Q hat? And then we can check our work on P hat, Q hat. So now what is Q hat? So now we know these values. Yep. And then Q hat's going to be what? Which Q hat's nice and easy once you know P hat or P naught. Those are different things. But if you know what P is, not P value, But if you know what one of the proportions is, whether it's the sample, the hypothesized, or the true, you can always find the complement of it by doing 1 minus. And then you check to see if it adds up to 1. Great job, Savannah, right there, and Sloan. Excellent work. So here's the thing, though. You can plug in all these numbers because the only thing you don't know here is you don't know what sample size they need for the full investigation. Now, they're asking to do a full investigation right here. They're not talking about the sample right here that was done, so we're actually going to remove this. They're actually solving for n. Okay, so this is where it gets a little bit interesting. We could make a confidence interval and find out the margin of error they have now, but they want to solve for n. They're not going to use that n to create this interval. So at this point, we do not know what n is. It's like, what n should they take to solve this out right here? So you can plug in everything and solve for n, but watch this. We're going to take right here and divide both sides by z star. And that gives us p hat times q hat over n square root. So we can get rid of the square root by squaring both sides. So this side becomes squared also. So that side's also squared now. Does that algebra make sense, yes or no? I divided both sides by z, so z's over there on the left, and then I squared both sides to get rid of the square root. How's that looking? Are we pretty good on that? Does that make sense mathematically? So we just did both sides divided by z, and then we squared. Yep, okay, cool. And then we are going to take and we're going to flip. A lot of people don't know you can do this, but you can flip equations. So I'll show this over here on the other side, like how it works conceptually. But now we're just flipping both equations. So we're just flipping both because if you had something like, let's say, this is just to show an example, like 2 over 3 equals 6 over, that'd be 9. You can flip it, and that would just be over here, 3 over 2 equals 9 over 6. And you can see these are still working out to be the truth right there, because 2/3 equals 6/9, and 3 over 2 equals 9 over 6. So those do still equal. So that is a mathematical trick I think a lot of people don't know, is that you can just flip equations. It's kind of cool how math works like that. So all we did was just flip them upside down. And the reason we're doing that is because now we can multiply by p hat, q hat on both sides, which brings that over to this side. So now we are multiplying both sides, which removes it from this side over here. Sorry, it keeps moving my mouse. But we have p hat, q hat, times z over me, and then we have the square, and look what we have over here. We have n. So guess what? Now all we have to do is what? All we have to do is what now? With all the algebra we did, all we have to do is what now? What's left for us to do? Just plug in the numbers. So if you look where your p hat and q hat are, we have p hat is 0.1 times 0.9. That gives us that value. We're going to take z, which is 1.6449, the extra decimal. I'll do 5 because I wrote that down. Divide by the margin of error of 2%. And then we're going to square this value right here. We're going to times it by the 0.09, and there's the value, and make sure to round up. And we should have it. And round up to the nearest number. Do not forget to round up. They put a little wiggle room on this question now. There's the answer. If you know how to do this question, you can get it right a lot of times. There's that value right there. So if you know the math, which don't memorize it, but you can go right here. And let's see right here, 6 divided by 50, that's 12%. I'll remember that. And so now we take the 1.96 divided by 0.02, square that number right here, times by 12, times by 0.88, and there's the number on the screen, rounded up, 1,014. Why does it have two answers? Why is this second answer existing? See, it has a plus or minus 1. But once you know the equation, you can just, like I'm doing the solve right here. Z-score of 95% confidence is 1.96 divided by 0.03, because that's the margin of error, square the value. 8, so that's 20%. Ooh, I lost my numbers. So 1.96 divided by 0.03. There's that. Square that value, times by 0.2, times by 0.8, and there's that value right there. Hey, Alexander, good to see you here. What is the problem in environmental agency from chapter 13? The direct mail? Yeah, let's do direct mail here. Oh, we're showing complete problems. Sure. Very similar problem right there. So you can literally just solve these out. So once again, this one, just to briefly mention this one you have to assume 50% because it doesn't tell you a sample proportion. We did this one yesterday. So it's a similar problem, but since we know 95% confidence, 1.96 divided by 0.06 times this, and then we go 0.5 times 0.5, and there's the value, 267. Once again, so if you know how to solve these problems, they're super quick, but it really comes down to notation. So these problems can be done just like that, but you have to know the notation. Okay, let's go find that direct mailing advertisement right there. Here we go. Okay, so Savannah and anyone in the chat, what's it going to boil down to with this problem? We're going to work this problem without looking at what they ask because we can probably guess how to solve it because it's all going to boil down to what? What's this question going to boil down to right here? And let me mark this in the video while you tell me. It's probably going to be knowing our what. We repeat this all the time. This is for people in the future who watch in this video. Notation, brother.
Notation, brother.
Always the notation. We have to know notation. If you don't mark the notation, if you don't know the notation, you're probably going to get stuck on this question. And you're going to say, well, what am I even solving for? What am I doing? And so direct mail advertisers. Direct mail. Sure. There we go. Advertisers. Okay. So with this right here, notation always, they like to send junk mail to thousands of potential customers and hope that they will buy some of the company's products. The response rate is usually quite low. So why is this categorical? Because someone responding is a yes/no question. Did people respond to the direct mail advertisement? Suppose a company wants to test the response rate, which is do people respond, and sends 1,030 people a randomly selected, the people are, from their mailing list of 200,000. We just checked what right here? That literally answers the question of what? The 1,030 people out of the 200,000 people they have in their population is that. If we do it as a percent, it's about 0.5% of their population. And they're randomly selected. They literally just checked what right here? They literally just checked what? They literally just checked what? Checked what off by saying, oh, we did random people, and then we only sent it out to about 0.5% of our people. So they literally just checked what for us? Think about what we always have to check to make sure we're doing these things properly. Well, so that's not p hat yet. That's not good. So that won't be p hat right there. The amount of people they sent to out of the population here, let's mark the notation. So that'll help us out right here. So that's not, we checked the randomness. Randomness is met right here. And then with the notation, that's n, and that's capital N, and this is x. So doing n over capital N and seeing that this is not greater than, less than or equal to what is what we're checking. We want the sample out of the total population to be less than or equal to what? So we want a randomly selected group of individuals, and then we want the sample to be less than what of the total population size. So we're not even looking at what my Pearson's asking us. We're remembering how to do these problems. Because less than 10%, great job, Sandra, right there. So this is less than 10%. You can do the mathematics to check because they sampled less than 20,000 people also. So that's another way of stating it, is that the sample needs to be less than 10%. They sampled less than 20,000. They sampled less than 10% of the population because their mailing list is all the people they care about. So they took a sample of 1,030 people. And then from the sample, 131 of them responded to it. And that makes that X. So what could we calculate now that we have X and N? So if we have X and N, we can quickly calculate this, which is like, okay, I have X, I have N. Now I know 131 people responded out of the 1,030. So I should calculate what here? Respond really quick. What can we calculate? Any ideas? We have X, we have N, we have the amount of successes out of a sample. So that is the proportion. And always try to make it like a simple problem. Like if I told you I talked to 1,000 people and 200 of them own a dog. Great job, Savannah, right there. If I talk to 1,000 people and 200 of them own a dog, what proportion of people own a dog? Just quickly with that right there to be like, oh, we talked to 1,000 people, 200 of them own a dog. What amount of our sample owned a dog, which is p hat? And so we're not exactly using those numbers, but this is the way to always like kind of remember how to solve it, is like use a simple example where the numbers are just like 200 people owned a dog out of the 1,000 people we talked to. So p hat right here is x over n, which is going to be 131 over 1030, and that is equal to p hat. And so let's take a look at that right here. 131 divided by there, and so 1272. And as soon as we get this, if we get p hat, we want q hat. So q hat is going to be 1 minus p hat. And once we get q hat, we want to make sure they add up to 1 right here, 0.8728. So just make sure these add up to 1. They should. Decimal differences might come into play. But we pretty much have everything we need right here, I think, now. One last thing to note is that we need n p hat to be greater than or equal to 10. And we need n q hat to be greater than or equal to 10. You can check this mathematics. But the thing is that n p hat is equal to x, and x is equal to 131. And just if you look at the equation right here, this is equal to p hat. So you could literally backwork it and see that n p hat is equal to x, just mathematically speaking. And this value right here is going to equal to n minus x. So n minus x, because it's the amount of failures we saw. So there was 1030. And you can always double check your work right here by solving it. I'll show the double check. But that's 899. And these should add up to n. And that's the success failure condition right there. How'd you get 131? Right there. Yep. And so, but you could also just plug in p hat, because p hat is this right here. And then you could times that by 1030. You see how that's 131, but because we didn't carry all the decimals, we don't get exactly that. You can take q hat and times it by the sample size and get this right here. But once again, some decimal differences come into play. It's just if you don't carry enough decimals, you won't get exactly 899. You won't get exactly 131. But we see we have passed the success failure condition. Now, let's go ahead and look at the question. I think the first thing it's asking us is for a 90% confidence interval. So when we do 90% confidence, we always put a star on the Z, because why? The star on the Z is relative to a certain percent confidence. So take a moment right here, go to the apps page. Thank you once again to Adam Spanbauer. And find me the Z statistic. That's why we put the star right here. And tell me the Z relative to 90% confidence. So this star means relative to a certain percent confidence. Go ahead and find me the Z relative to 90% confidence. Great job, Sloan, right there. Automatically given the answer. We love that right there. So let's show how Sloan got that. Make sure you're over here on the normal curve. You'll want to be here on the normal curve. Then you want the mean and standard deviation to be 0 and 1, because there's z-scores now. Area is 90% in between. Make sure you've clicked all of these right here. Look at my screen, check your screen. Then you want to find an x using a p-value, and this gives the z-score for 90% confidence. And what I really love about this is if you change this to like a standard deviation of 2, it no longer calls it a z-score, because it's not. Z-scores are only for the standard normal. Good to see you here, Sam. So 1.645 right there is the z-score. And if you look, now we have all the other components. We have everything we need, 1.645, square root, and then we're going to put in the numbers right here, 0.1272, 0.8728, and then over, and then 1030, because that's the sample size, plus or minus 0.1272. So with all these values right here, we just start plugging in the numbers, 0.1272, 1 minus times divided by 10.3 square root 1.645. If I really knew how to type, and that's the margin of error. So I always pause when I solve the margin of error, because I'm going to put it here for the problem, 0.171. That's the margin of error. And then we go right here. And now let's solve the rest of it. We're going to go right here, 0.1272 plus this, 0.1443. And now we subtract. And 11012. There we go. Great. Sloan, thank you so much. Sloan, 500 points. That's a huge help for me to see it in the chat because I'm not going to have the chat up, and that's a good check on your work to make sure you can solve these and know how to get these problems correct every time. And now look, it wants it as percent, so we have to times these by 100, and it says to 1 decimal, so that's going to be there. And then we go right here for the next one, and we go right there. So make sure to times by 100. So Sloan's numbers right there are just going to be multiplied by 100, and then check your work. I'm going to trust Sloan on this one. Explain what this interval means. This is where we don't read their interpretations. We give our own interpretations. I am 90% confident that the true proportion of people who respond to the flyer is contained in the interval blank to blank. So the company is 90% confident that the probability of a randomly... No, not a person. The company is 90% confident that the percent of people who respond to the flyer is contained with the intervals. That sounds good. Now, they use the word falls. Ooh. I don't like that falls word. I never like that. Because falls is active on the truth. The company is 90% confident that the percent of people who respond to the flyer falls within the confidence interval's bounds. Oh, no, it's... I don't like that they say falls. We might have just enough time right here. Yeah, I think we do. Let's see. Explain what 90% confidence means. Now, we talked about this in the last one where Enes sent us out this really great app right here to show us, or yeah, it's applet, I guess, to show us how 90% or this is 95% confidence intervals work, is that 95% of 95% confidence intervals will contain the truth. Like this one didn't, but in the long run, and this is not long run enough, law of large numbers, we will see the truth contained in the interval 95% of the time for 95% confidence intervals. And these are all different intervals. That one did not contain the truth, and that's where y bar is at, and the plus or minus is the margin of error, and that's the truth right there. These are intervals to estimate the true mean. So each of these, center of the interval, is a y bar plus or minus some margin of error. Notice how some have larger margin of error because they have a larger standard deviation from the sample they were taken from. So right here, 90% of all random samples will produce confidence intervals that do contain, right here. How is it not C for the multiple choice on the previous one? It's not a person. It's not about a person right here. It's about the truth, because this is about one individual responding. It's about the true proportion. I wish they said that. Like, once again, I don't always love their interpretations because I would say I am 90% confident that the true proportion of people who will respond to the flyer is contained within the intervals. I don't like the word falls. That's not a good statistical word. I've had a lot of stats professors complain about that because the truth is not an active word. Our confidence interval might contain the truth. The truth does not actively fall somewhere. Good to see you, Alexander. The company must decide whether to do a mass mailing. If the company can show that it gets at least 5% return, they will do the mass mailing. Do you think the company will have at least a 5% return on this, Sloan, and why? Do you think they'll have at least a 5% return? So if they have at least a 5% return, they will do it. Do you think they'll get that? What do you think? Will they get at least a 5% return? What would you say? You're the person talking to the company. You say, I'm 90% confident the true proportion of people who respond is somewhere between 11% to 14.4%. So do you think you're telling the company we will get probably more than 5%? Does it sound like we will get more than 5%? I would say yes, because the entire interval is above 5%. So we have reason to believe more than 5% of people will respond. And good question. Except for the fall word, that's my only qualm with this question right here. And so Will has in December, I think we did that one. Will. So we might try to do, let me look at the notes right here. I think we did that one. Wait, no, we did all these dates. Oh, we didn't do that one here. So we might not do the waist size one because I might go and eliminate that one. Oh, and I said chapter 13 right here. This is, or I said 14. This is 13. I think environmental agency is 13 also. Okay, cool. Okay, so now in December 2012, a poll taken. And thank you everyone for being here. Statua 1, Chapter 13 quiz in a poll taken. Okay, let's go check out that one. In a poll taken, oh, we already did those. Have you done the during routine screening? I don't think we have yet, Micah. Thank you, Micah, for being here. 100 points. Might have just enough time. Someone wants to meet with me about... here we go. We'll try, we can do a few of these. We'll speed run these. So we're going to do some speed runs here. Stat 201 speed runs. I used to have that video where I could pull it up. So the first thing it asks us right here is a margin of error. Sounds great. Okay. Here we go. Sounds great. Sounds great. See you then. I have a meeting in 9 minutes. So we're going to speed run these. Here we go. Time for some Hacker Man right here. Let's put a little Hacker Man on and speed run these. Here we go. Stat to 1 Hacker Man time. Time for speed run. Here we go. So here we are with a poll taken in 2012, asked 1,006 people, which is the sample size, whether they're baseball fans. 48.1% said they were. Almost 5 years later, they did another poll, and they found that 34.7% of a smaller sample size had reported being baseball fans. Okay, so the first thing it wants us to do is do the margin of error. That's going to require a little bit of math. I thought it was super quick. Find the margin of error. Okay, let's go do it. So it all boils down to notation right here. Notation, notation, notation.
Notation, brother.
Okay. I'm on the clock. Slow and timey. You ready? Okay, here we go. Margin of error. Ms. P hat. And we know that 90% confidence interval is 1.645. Check out the previous problems where we found that using the apps. Throw apps on the screen, Sloan, for 100 points right there. Sloan's helping me out with the speed run. Sloan's going to show you where the apps are at. P hat is this for the first one, so that's 0.481. Complement of it is going to be 0.519. Sample size is 1,006. Sloan right there. Great job with those apps. And that is going to be the margin of error of the interval. So 481 times 519, that's the complement, divided by sample size. Oh, yeah, it is a 6. I almost did a 9. Square root of this, that's the standard error of the interval. Almost said a wrong word. And there's that. So it should be the margin of error of the interval. And so here, round to 3 decimals, we should have it correct, unless I did an error. So what this means, one is 90% confident plus or minus margin of error, the true proportion of adults, that sounds accurate to me, is equal to the polls. No, that sounds weird. Come to the true proportion. No. One is 90% confident that this poll's estimate is within plus or minus of the true proportion. Yes. Yes. We don't put plus or minus on the 90%. There we go. That's right. I think I missed this one on a previous day. If we wanted to be 99% confident, that would make the margin of error larger, just to show that conceptually. I know we're speed running here, but if you go more confident, the interval gets wider. This is a t-interval technically, but the interval does get wider when you increase the confidence. So to be more confident, the interval would need to contain the truth more often, so the interval would be wider. Contain the truth more often would be larger. Find the margin of error for 99. Well, that's just going to change the z-score. So the z-score has to change right here for 99% confident. And so the z-score is 2.5758. Check out the applets on the screen. So we just have to resolve this. What we could do is we could take the ratio of 2.5758 over 1.645 and then multiply our interval by that. That's kind of a quick resolve of it. So I'm going to take this right here, 2.5758, divide the original one by this. There's the ratio of the numbers times the standard error by that, and it's 0.41. Now, once again, I wouldn't suggest solving this way. That's just some math trickery. In general, false will smaller margins of error produce smaller margin of error is less confident. So there we go right there. And we did a longer solve of this on a previous day. So check out, I think yesterday we did a much longer solve of this. And I just did some conceptual solving right here to get the answers. Thank you. Yeah. And what's even better is if I could just use R or things like that, I can literally get t-intervals in seconds just by putting in the data and just doing that. That's usually how we do a lot of statistics, but we need to know what we're solving. It's not about solving questions. It's knowing what you're solving and why you're solving. We had one more question right here. We're going to speedrun it also during routine screening. Okay, we got to do this one even faster because I'm going to have to go to the meeting here in a moment. Thank you so much, everyone. So this is another speed run of Stat 201 Chapter 13 quiz during routine screening. Okay, let's go check out during routine screening. And we have to do this one also in just seconds right here. During routine screening, speed running the question. Thank you, everyone who comes by office hours. We do as many as we can. Sometimes we go quick, sometimes we go fast. Different ways of learning. Where's that during routine? It's going to take us more time to find the during routine screening. It might literally take us more time to find the question. Is it a homework question? It might be a homework one. Oh, is it one of these back here? Yeah, we did this one earlier. Check out the longer solve on this one. So Sloan, you ready? Here we go. 3, 2, 1, let's go. 2.575, no. 2.5758 divided by this right here. And then we square it. And then we see right here that this is 27%. So that's going to be times 0.27 times the complement, which is this. There we go right there. We round it up to the nearest whole number, which is going to be 4. Check answer, and we got 100. So there we go right there. This is very similar to, you can search the question up. Check out the other questions we did earlier, which are marked in this video, just shy of 20 seconds. Yeah, I made a typo at the start. I could have done it in 15. But that question is very similar to this one right here. So if you're watching this and you're wondering how we solved it, we did a 10-minute solve of that one earlier. We're going into much more detail. With that, I've got a meeting here in 2 minutes. So until then, bye for now, everyone. Thank you for all the great work. Check out the rest of these and think about how to solve them, which is key. Mark your notation and swing office hours and ask questions. Bye for now. Bye. You're welcome, Sloan.